more today. Just to show that it is, you know, I mean, you have it, why not use it? So, alright, so we're going to find some relative extrema, meaning that we're only going to go for the first derivative. So, g of x, this function g of x, it looks kind of like a product of two functions of x. Yeah, that's strange. I can't say that that pen looks blue, but I guess it is. Right. Okay, so this appears to be a product. I mean, it is a product, but so we can label the first part of this product A. Now it is possible to leave that 3 sort of off to the side and incorporate it back into whatever you get just at the very end, right? Because that 3 is a constant multiple. But there's no reason that you couldn't make it part of A as well. Now, if that's A, then this is B. So using the product rule, we want if A is 3x squared, if we let A be 3x squared, A prime would then be 6x from the power rule, right? You take that 2, put it in, multiply it out in the front, 2 times 3 is 6, decrease the power by 1, then that's just x, so 6x. B, being 1 minus x squared, the derivative of that, derivative of 1 is nothing, and the derivative of minus x squared is going to be minus 2x, also from the power. That 2 would get multiplied in front, be a negative 2, power would decrease by 1, you get minus 2x, or negative 2x. Now with the product rule, all you have to do is multiply these two together, add whatever those products are. There's no denominator or anything like that, there's no squaring. So it actually doesn't matter which one you start with, as long as you multiply them by the opposite, the opposite part's derivative. As long as you put these two together and these two together, it literally doesn't matter what order you write it in. But we'll start with A prime, just because. Okay. So 6x times 1 minus x squared plus say 3x squared times negative 2x. And so this is what g prime is going to be. Okay, so distributing this, just to simplify it, and multiplying these two together, it'll give you, 6x minus 6x cubed. And this part, multiplying these two together, that'll give you negative 6, and x squared times x is going to give you x cubed as well. So this just becomes 6x minus 12x cubed. Now, technically speaking, using the product rule wasn't really necessary, because it is possible, because these are both polynomial, A and B are both polynomial functions. It is possible to incorporate them sort of into each other to make something actually worthwhile. Which would not be the case if, like, A was algebraic and B was trigonometric. There's no way to really combine those into anything that means anything. But since these are both polynomials, you can actually just, g of x being 3x squared times 1 minus x squared, you could just distribute this, getting yourself 3x squared minus 3x to the fourth, and take the derivative of that instead, and get, as if by magic, 6x minus 12x cubed, power rule for both terms, which is the same derivative as you got this way. So either way, that's the derivative, right? And so it's this derivative that we're going to set equal to 0. So g prime of x equal to 0, or set it to be undefined, or try to find where it's undefined, in order to find the critical values, the critical numbers. So 6x minus 12x cubed equals 0. Now, from each of these, you can factor out, I suppose, 6, okay, and you can always factor out the lowest power of any variable or any factor that appears in all of the terms. So the lowest power of x, so x is in both terms, and the lowest power of x is 1. So you can factor out 6x. And if you do that, factoring a 6x out of 6x is going to leave you with 1. And factoring out a 6x out of negative 12x cubed is going to leave you with minus 2x squared. Now, since this is a polynomial, you sort of treat it like a polynomial and set each factor equal to 0 in order to solve for your solutions, right? Which in this case are going to be the critical numbers. Setting this x that's out front to 0 is just going to give you the critical number x equals 0. Whereas setting this other factor, 1 minus 2x squared, equal to 0, is going to give you, I suppose you could add 2x squared to both sides. 1 equals 2x squared. Divide by 2. You'd get yourself 1/2 equals x squared, which, if you take the square root, gives you x equals plus or minus, right? Because whenever you do the square root as an operation, there's a plus or minus, gives you plus or minus the square root of 1, which, is there one? Yeah, so like you can also write this as 1 over the square root of 2, or if you were to rationalize this by multiplying both the top and the bottom by square root of 2, you would find that this is actually equal to square root of 2 over 2. Is that... but, there's no problem with leaving it as the square root of 1/2. Especially because in everything that you're going to use it in, it's going to get squared, and so why not just leave it as a whole square root like that. So those are your 3 critical numbers. So putting down those 3 critical numbers, 0, the positive square root of 1/2, and the negative square root of 1/2. square root of 1/2, which again is equal to 1 over the square root of 2 or square root of 2 over 2, is valued at around 0.7. So a good test value for, say, I'll just start from the left. So a good test value between negative infinity and negative 0.7 or whatever, it's probably negative 1. And between negative 0.7 and 0, maybe negative 0.5, say 0.5. And positive 0.5, positive 0.5, and positive 1 are probably good test values to be having. Now, in order to do the first derivative test, you just plug these into g prime, which is right here. So rather than spending time evaluating these by hand, there's definitely no reason that, if you're confident in your ability to input things correctly, sort of the way that you mean them on a calculator, that you couldn't just evaluate 6x minus 12x cubed, right, for a particular value of x on the calculator. It's 12. X is negative 1 cubed. Right, so plugging in negative 1 into g prime gives a positive 6. Now you're not so concerned with the fact that it's 6, you're concerned with the fact that it's positive. And we're talking about the first derivative, so that's going to tell us that this is increasing. For the original function is increasing. And then you would just do the same for the other test values. Now, if you have a graphing calculator, and possibly even if you have a scientific calculator, it's possible to sort of not have to rewrite everything that you just put in. So definitely on a newer calculator, you can sort of use the arrow keys to scroll up and grab something that you typed before. But even if you don't have that, if you notice a function called entry in the random calculator, possibly above a button or something like that, you can press second and entry just to put out the last thing that you typed, the last thing that you pressed enter on. And and once you have this, if you become comfortable with using the delete key and its secondary function, insert, it is possible just to not have to, if you're not used to it, it can seem like more work. What's up? Yeah, so you guys will be able to use graphic calculators on this test. Yeah. Oh yeah. So not exactly, no, but here, hold on. Okay, so that's negative. So g prime of negative 0.5 returns a negative result for g prime, which means that it is decreasing.
Has there ever been a problem where it was increasing for two variables?
Yeah. Has there been or can there be?
Has there been?
Maybe. I don't know.
That would be it can be?
Yeah.
Like the one where it kind of just does nothing?
Yeah, there are several kinds of those things. you might have a equation that does this, like, if you think about how just the very basic x cubed function acts, y equals x cubed, it increases, flattens out, and then increases again. So that's a possibility. That's okay. All right.
I think it has to be fine erasing.
No, that's just the kind of eraser I never use. That's really misbehaving today. There's also this kind of function.
Oh.
Anyways, so these are the test values. It's increasing, decreasing, increasing, decreasing. So it appears as if here, when it goes from increasing to decreasing, you can sort of tell by the shape, that's going to be a maximum. Here, where it goes from decreasing to increasing, that's going to be a minimum. And at the third critical value, where it goes again from increasing to decreasing, that's going to be a max. So there are maxima at negative square root of 1/2, comma, whatever we're going to get when we put that in, and at positive square root of 1/2, comma, whatever we get when we put that into the original function, g. And there's going to be a minimum at 0, comma, whatever g of 0 is going to be. So in finding those, we just plug those back into the original function, g, right, in order to find the corresponding y value. So g of negative 1/2 is, and again, there's no reason that you couldn't use your calculator to do this. Negative square root of 1/2 squared times 1 minus the negative square root of 1/2 squared, close that, parentheses, and actually let me use brackets for this instead, just to, yeah. So the square root of negative 1/2, no, wait, the negative square root of 1/2 squared is actually just going to be 1/2. And there's going to be 1 minus, also 1/2. And actually, there's no reason that you can just let's not make this harder than it has to be. 3 times the negative square root 1/2 squared. Nope. Should not be under the okay. There we go. 3 times the negative square root of 1/2 squared times 1 minus, and again the negative square root of 1/2 squared, and close that larger set of parentheses. Should be 3 volts. And it's going to be because it's going to be 3 times a half times another half. So 3 times a fourth, that's 3/4. So that y value is 3/4. In fact, even when you take off the negative sign, since it's being squared every time, it actually comes out to just be the same thing. 3/4 for the positive square root of 1/2 as well. The y value there. And when you plug in 0, you can sort of see it just by looking at it, but it's going to be 0, because that's going to be 3 times 0 squared times 1 minus 0. This is 1, but you're going to be multiplying it by 0, like right in the middle here. So that y value ends up being 0 as well. So this last one that's actually going to be printed on your paper is it's an optimization problem, but it's certainly not one of the worst ones. So in every optimization problem, there's going to be both a primary equation that represents the quantity that you're looking for, the quantity that you're looking to maximize or minimize. It represents what to maximize. And there's going to be a secondary equation that represents some sort of constraint or condition that you're going to be restricted by. So if you just sort of skip to the end of the question, it looks as if what you're trying to maximize is the enclosed area of this sort of shape, right? And so describing the enclosed area in terms of what's there, you can describe the enclosed area as, well, this is a rectangle, so all you need to do in order to describe the area is take the length and multiply it by the width. Now the length is 2x. And the width here is y. So you can just describe the area as 2xy. Now, of course, we want to maximize that, but it's going to be difficult to take the derivative if this function is going to be in terms of both x and y. It's not really something that we do very often to take the derivative of a function within 2 variables. So what we can hope to do is to use a secondary equation, which, if you go through the problem, this restriction appears to be that he's limited to using exactly 200 feet of fencing in order to construct this. And so taking that and looking at the shape, the secondary equation should be that some expression is going to equal 200 feet, right? But describing the amount of fencing used in terms of the variables here, that's going to be 4 lengths of x plus 3 lengths of y, because it's not labeled, but this middle length is also of length y. So there are 4 of these x lengths and 3 of these y lengths. So now what we're hoping to do to the primary equation is to get it all in terms of one variable, generally speaking. x. I mean, you could theoretically do y, but, you know, why mess with, you know. So we want this to be in terms of x only, which means that we're going to want to replace this y. So if we want to replace y with something, well, we better take this and find an expression for y using the secondary equation, meaning that you'll want to get y by itself. So if you try to get y by itself here, we'd subtract 4x first thing. Giving us 3y equals negative 4x plus 200. And then just let's divide by 3. And that's going to give us y equals negative 4/3 x plus 200/3. Right, that completely washes it out. Okay. So this is an expression for y in terms of x. So what we can do with that is to take this and replace y in the primary equation with this expression. So when we do that, what that ends up being is a is equal to, that 2x is still there, but y gets replaced by this equivalent expression, negative 4/3 x plus 200/3. So that now this area function is no longer in terms of both x and y, it's just in terms of x. So, I mean, you could take the derivative like this, I guess. I mean, you could use a product rule, but what would be easier is probably just, you know, simplifying it by distributing 2x to both of these terms. So 2 times negative 4/3, that's going to be negative 8/3. And x times x will be x squared. Alright, that takes care of the first term, and so 2 times 200/3 will simply be 400/3. And there's that x. There's no x here, so that just ends up being 400/3 of x. So now that's the function for the area in terms of x. All good and ready to take the derivative. So what you're looking to do is you're wanting to find the maximum of this function. You want to find the maximum of a. Now at this point, it's pretty much just stuff that you already know. You know, the questions from before, you were given the function, and it's to find the maximum. You take the derivative, set the derivative equal to 0, round to 5. You know, critical numbers and all that stuff. But now, you know, we're at the stage where, you know, we have that function. So if we take the derivative, a prime, you know, we can call it a prime, we can get there using the power rule. We'll take this power here, multiply it in the front, and then subtract 1. That'll give us negative 16/3 x, right? Just x, because it used to be x squared, and its power got reduced by 1, so it's just negative 16/3 x. And the derivative of 400/3 x, well, the derivative of any constant multiple times x will just be that constant multiple. You know, the derivative of 2x is 2. The derivative of 10x is 10. The derivative of 400/3 x is 400/3. So that's a prime. Okay. Now we want to find the critical numbers of a prime. And those will occur whenever a prime equals 0, or possibly when a prime is undefined, but we'll see if that happens. So if a prime equals 0, that means that -16 x plus 400 because that's what a prime is, equals 0. Now, in order to simplify this a bit, we could just multiply both sides by 3. You can also, move terms first. Yeah. So we get -16x plus 400 equals 0. And you can see after adding 16x to both sides that we're really just looking for something that, if we multiply it by 16, ends up being 400. And if we divide that by 16, we'll find out what that is. That is 25. So x is going to be 25. That's going to be our critical number. And as for where a prime is undefined, it is undefined nowhere, so no critical numbers come from that. Now, we have the one critical number. And the implication in the problem that there is just the one maximum, and probably no minimums. You can probably surmise that the maximum is going to occur at x equals 25. And it will. But if you wanted to make absolute sure, you would list it as a critical number, pick a test point or a test value on either side, maybe like 0 or 50. I mean, you could even use 24 and 26 if you wanted. And just try to evaluate a prime at 0 and a prime at 50. And if you do that, if you plug in 0 into a prime, that's going to disappear and you're just going to get 400 which is positive, meaning that over this interval the function is increasing. Right? If f prime is positive, or if the derivative is positive, that means the original function is increasing. And if you plug in 50, you'll get a positive value, or no, you'll get a negative value. Yeah, that's right. What? Yeah, you'll get -400, I guess. But again, the value doesn't really matter. What matters is the sign. So get a negative derivative there, meaning that the original function is decreasing, and if you needed it, that's verification that at 25 there is a maximum. At x equals 25 there's a maximum. Okay. Now, it was possible to just sort of look at the function a right here, the area function, and determine, well, it's the downward-facing parabola, which has this sort of shape. So it can only have a maximum. And that maximum occurs exactly where there is 0. And so, like you can even do that and say, well, x equals 25 is surely going to give a maximum, right? Because this is a downward-facing parabola. But anyways, so x equals 25 is where the maximum area occurs. And so that gives us an answer for x, but it doesn't exactly give us an answer for y. I'm just gonna label all the x's here. It doesn't, you don't really have to do this, but so x equals 25 is the value of x that's going to give the maximum area. Now you could go up here, say, okay, well there's 200 feet of fencing. X being 25 means that 100 feet will be used up, meaning that I have 100 feet remaining that I can spread among these 3 vertical, fence lengths, so that each one must be 100 divided by 3. You could do that and get y that way. But you could also use this expression for y up here. Y equals negative 4/3 x plus 200/3. That's the expression for y that you made out of the secondary equation. So if you plug in the value that you know x to be, which is 25, you can also get 100/3 that way. Because, let's see, negative 4 times 25 is negative 100/3 plus 200/3. And adding those together, since the denominators are the same, is just going to give you 100/3. So x is 25 and y is 100/3. So you could reason that out, mathematically using this, or it'd be no problem if you also reasoned it out using the diagram as well. They represent the same thing, just one's a diagram and one is a equation. Okay, so that's the last of what you have written, of what you have printed. So I've tacked on some questions to this document here that aren't going to be printed, on your printed copy. You can just write these down, the back of the back sheet. Yes. These are just going to take up 1 page, right? In fact, you don't even have to write this whole problem if you want to. You can just, if you wanted to, you could just write literally this thing, just MVT the mean value theorem, for this function on the interval 1 to 2. Like, you could just write this if you wanted, and we'll go through the steps, but you'll know what they mean when you do them. 2x cubed, sorry. Yeah. No, I know. Yeah. Okay. So there are only 3 of these, so you can just jot this down if you'd like. And we'll take a... Okay. So the reason that we are going to be able to use the mean value theorem, the reason it is going to turn out, is because f is continuous. This function 2x cubed is continuous over the interval. It's continuous everywhere, but in particular, it's continuous over the interval 1 to 2, from x equals 1 to x equals 2. So f of x is continuous. And not only is it continuous, it is smooth enough to be differentiable over the entire interval. Also everywhere else, but in particular, it is differentiable on the interval from 1 to 2. Differentiable. Okay. Now, what you're wanting to do is essentially, so here is the interval from 1 to 2. Okay. And you don't have to draw this many lines. Just go up to 16. So this is what the function looks like. The function looks like this. It looks like... Oh. Boy, I'm not having a good time with this. Alright, let's just say it looks something like that. That is probably good enough. Okay. Now what you're concerned with is the interval from 1 to 2. Let's just pretend that that's how it's shaped. Alright, so what you're concerned with is the interval from 1 to 2. Now what you want to be doing is calculating the average slope from this endpoint, wherever it happens to be, to this endpoint, wherever that happens to be. So that's going to be the straight line connecting these two points on the function, the points at the endpoints of the interval. So 1 is A and 2 is B. So A equals 1. So f of A, you're just going to get that by plugging in 1 into the into f of x. So that's going to be 2 times 1 cubed, which is going to turn out to be 2. So you can sort of see this first endpoint is at 1, 2. And if b equals 2, right, it's the right endpoint. F of b is going to be f of 2, right, just plug in 2 into the function. 2 times 2 cubed, which 2 cubed is 8, and times 2 is going to be 16. So you can sort of see it's at a height of approximately, well, it should be exactly, but 16. So you're basically going to be putting it together. Oh, also, this should be b minus a, okay, rather than a minus b. So this is simply the same as, y2 minus y1 over x2 minus x1. If you plug all these in, 16 for f of b, 2 for f of a, 2 for b, and 1 for a. You should get 16 minus 2 on the top, right? That's f of a minus f of b over b is 2, a is 1. No, I wrote the bottom wrong. I wrote a minus b on accident. Yeah. Whichever way you write it, the order should be the same on the top and the bottom. It should be like b, then a. I mean, you could theoretically do a and then b as long as you do it both times. Yeah. So that's going to come out to 14 over 1, or just 14, meaning the slope of that line is 14. right? I mean, even if you think of it in terms of rise over run, it goes up by 14 units and goes to the right by 1 unit. So the slope of that line is 14. And that slope represents the average value from one endpoint of the function to the other endpoint of the function. So the average slope, right? The average slope across the interval is 14. And so what you're looking for is some point on the function where the tangent line has that same slope, right? Here won't work, like, for example, here won't work because, that tangent line is going to be, obviously I'm exaggerating the difference, but that tangent line is going to have the wrong slope. Here won't work because that tangent line is going to have the wrong slope as well. It's not going to be the same slope. But there should be somewhere in the middle where a tangent line has the same slope as that secant line. And how we're going to find that place where that happens is we're going to take f prime and set it equal to that average slope. So we're going to take f prime and set it equal to 14. Now, if the original function f is 2x cubed, then f prime should be 6x squared, right? Just from the power rule, right? Take that 3, multiply it out in front, that makes it 6, and decrease the power by 1, that makes it 6x squared. So you can subsequently solve this for x, or just divide both sides by 6. You're going to get x squared equals 14 over 6 is probably better represented as 7 over 3.
One question.
Yes.
On C grid, take the derivative. Is it on F prime?
Oh, it's no.
So why did you say like value F prime is X?
So you don't actually need to know what f prime of x is in order to know what its average value is. You do need to take it in order to find out where it is at any particular point, but the average value of the derivative is given by the slope of the secant line, like the line connecting the two endpoints. Yeah. So if we take the square root of both sides here, we'll get that x can be the negative square root of 7/3 or the positive square root of 7/3. Except the negative square root of 7/3 is not on the interval from 1 to 2. It's not in between 1 and 2. Whereas, if you wanted to confirm that the square root of 7/3 was, it's valued at about 1.53 or so. So that is between 1 and 2. It is on the interval. The square root of 7/3 is on the given interval. So that's that x value, that sort of mysterious x value. That's the exact point on the function where the derivative at exactly that point is going to match the average slope from one endpoint to the other. And it's the only place that it does so. So basically, after you confirm that a function is continuous and differentiable, you sort of set up an equation where on one side you got the average slope given by this sort of, the slope formula, basically. The slope formula for the two endpoints. And on the other side, you put, like literally what f prime of x is, like the equation for f prime of x. So that you can solve for where the instantaneous derivative, where the instantaneous slope matches the average slope. The instantaneous slope being the derivative, and the average slope being whatever number comes out of it. So for the second one that you also don't have, you don't have a printed copy of, you want to find all relative extrema of this function, basically. Right, just the relative extrema of x to the power of 2/3 minus 6. So this is a radical function. But we're only going to have to take the first derivative. And it's already written as a rational exponent, so we'll take the first derivative, set it, find out where it's either 0 or undefined. Those will be our critical numbers, and sort of work with those critical numbers in the usual way. So in order to find f prime of x, we can just use the power rule, because this is already written as a rational exponent. So in order to do that, we just take this power, put it in the front, and decrease the power, and then decrease the power by 1. So that'll give 2/3 x, and 2/3 minus 1 is going to be negative 1/3. Of course, if you're not really good with fractions, you can always just type 2/3 minus 1 to the calculator and express it as a fraction. And the derivative of minus 6 is nothing. So that is the derivative of f. Now, it might be easier to think of where this might be undefined or 0 as f prime if you were to rewrite this in a couple ways. So first, this negative exponent. The fact that this negative exponent is here means that you can send it to the denominator as a positive 1/3, but on the bottom. Right, so 2 over 3x to the 1/3. Then next, instead of writing as a rational exponent, instead of writing 1/3, right, as a rational exponent, you can actually change this to be the cube root of x instead. Okay, so with that, it might be easier to think of where it's 0 or undefined. So that's just, f prime rewritten in a different way. So we find our critical numbers by finding out where f prime equals 0, or where f prime is undefined. Now, if you tried setting this equal to 0, you might find that it's impossible for that to equal 0. That numerator is always a 2, and 2 divided by anything will never equal 0. I mean, you can get it to be really small, but you can never get it to be 0. in particular because it is impossible to set the top of that expression to be, to get the top of that expression to be 0. So this will never equal 0. So this equals 0 nowhere. Now, as for where it's undefined, you can sort of tell by looking at that expression that 2 over 3 cube roots of x will be undefined whenever the bottom of this is 0. And as for what makes the bottom of this 0, well, all we need to do is find out where the cube root of x equals 0, which only occurs when x equals 0. So if x equals 0, f prime is undefined because trying to plug in 0 into f prime will give you 2 over 0, which is an undefined expression. You can't divide by 0. So critical numbers can come from where f prime is undefined. We didn't have an example of that before, but now we do. But now you have your critical number. And it is 0. And it's only one critical number, so there are only going to be 2 intervals that you have to test. And because this is 0, then the best value for the left interval is probably going to be -1. And the best value for the right interval is probably going to be +1. So for the left interval, you'll want to test -1 by plugging in -1 into f prime, which just means evaluating, well, not even really evaluating, but just thinking about the sign of 2 over 3 cube roots of -1. Now, the cube root of -1 will be -1. -1 times 3 is a negative. So the bottom is negative. A positive divided by a negative will be negative. We don't even really care that it becomes negative 2/3 or whatever. All that matters is that it's negative. Now if you do the same for 1 on the right hand side, 2 over 3 cube roots of 1. I mean, that's just a quotient product and all that stuff of positive numbers, so this is going to be positive. So this information from f prime refers to whether the original function is increasing or decreasing. And the fact that it's negative on the left means that the function is decreasing on the left and increasing on the right. So that it looks like a minimum exists right here. That this is a minimum. Of course, you could have guessed that by the implication that there was only a minimum and that your only critical value was 0. But, so at 0, you've got this minimum. And if you want to find the corresponding y value, just plug 0 into the original function. 0 to the 2/3 minus 6, 0 to any power. I suppose maybe aside from the power of 0 itself. 0 to the 0? 0 to the 0 can equal a lot of things, depending on what you need it to do. And there are ways to get there using limits, depending on if you're thinking about x to the 0, or 0 to the x. Because, 0 to any power is 0, supposedly. But also anything to the 0th power is 1, supposedly. So, which one is 0 to 0?
This one says I'm going to one, but no, it's not.
Yeah. There are YouTube videos about it. Anyways, so 0 to the 2/3 is nothing. So this just ends up being -6. So your y value is -6 when you plug in 0 to the original function. Now, as for why f prime was undefined, these functions that look like they're to the 2/3 power, they tend to have a particular way that they look. Okay, so let's do x to the 2/3 up here and -6 out here. So it has this sort of like double-sided sort of kind of bouncy kind of thing. And if you were to zoom in on this this place right here, this place where it seems to exist at 0, -6, you might see that it sort of does this sort of bouncy thing where it has this sort of sharp point. And so even though the original function exists there, at 0, -6, it's impossible to actually evaluate the derivative there, which is why f prime of x is undefined there and why it was one of our critical points. And last, we have this rational function, which we're going to try to analyze the concavity of. Now, this is a rational function. So in order to take the derivative, we'll use the quotient rule. We'll label the top as A and the bottom as B. And although this is a rational function, the derivative won't be so terrible because the degree at the top and the bottom are both 1. And it'll be a lot simpler than maybe some ones that you've seen. So if A is x plus 4, that means A prime will simply be 1. The derivative of x is 1 and the derivative of 4 is nothing. If b is x minus 7, b prime will also be 1, because the derivative of x is 1, and the derivative of -7, or minus 7, is nothing. Now in the quotient rule they go together like this, just like in the product rule, but in the quotient rule specifically, the order matters. There's and also there's some other stuff. So A prime goes first in the quotient rule. So A prime, which is 1, gets multiplied by the original B, which is x minus 7. And I'll just put B prime first in the second term. 1, B, which is B prime, gets multiplied by the original A, which is x plus 4. And all this gets placed over the original B squared. That's the quotient rule. Now, if you wanted to simplify this, you could, distribute the 1, but also that just sort of does nothing. You could, I guess, expand the top, right? So the top will be x minus 7 minus x minus 4, because this minus gets distributed into this second binomial here. Right? We have a minus sign in front of a binomial. Make sure that every term in the binomial gets subtracted, or essentially that the sign of everything in the binomial is going to switch. Right? Every term, not just the first one. But anyways, so it turns out that this x and this minus x right here are going to cancel out, and it's going to simplify to just -11 over x minus 7 squared. So that's f prime, but we're trying to analyze the concavity, which means we want the second derivative. Now, you could take the derivative of this using the quotient rule, with negative 11 as your a, it's the derivative, that will be 0, and x minus 7 all squared as your b. You could do that. I mean, that would be good practice if you need to practice quotient rule. But you could also, if you wanted, rewrite this as negative 11 times x minus 7 to the negative 2 power instead, right? So flip up that x minus 7 to the 2 up to the top as a power of negative 2. And now you can just sort of do the power rule and change the line. Because that negative 1, that's just a constant. So in looking for f double prime, and of course if you're not comfortable with that, you can just you can still use the quotient rule on this. But basically what's going to happen is that this is going to get multiplied to the front, giving us negative 2 times negative 11 is going to be positive 22. And according to the power rule, the power of this should be decreased by 1. So flip the power to the front, the inside should stay the same when using the power rule, and decrease the power by 1. So now it's to the negative 3 power. And according to the chain rule, we should multiply by the derivative of the inside, but the derivative of the inside, which is x minus 7, the derivative of that is just 1. So it actually doesn't really change all that much. So that's f double prime. And if we wanted to rewrite f double prime, we could write it now as 22 over x minus 7 to the positive 3, but on the bottom. Might be easier to see where it's 0 or undefined there. So your critical numbers are going to occur whenever f double prime is 0 or f double prime is undefined. Now, if you try to take this and set it equal to 0, you're going to run into the same problem as the previous question. The top of that expression is 22, and 22 divided by anything is never going to be 0. So this is equal to 0 nowhere. However, it is undefined at a particular place. This is undefined whenever x minus 7 equals 0, or at basically x equals 7. So that is your critical number, x equals 7. And you can sort of see it looking at the second derivative. Plugging in 7 would make the bottom 0, right? 7 minus 7 is 0, 0 cubed is 0, you're going to get 22 over 0. If you try to plug in 7 as your x value, then your cavity is at. So your only critical number is x equals 7. And so you just have to check the concavity to the left, maybe at 6, and the concavity to the right at 8, maybe, by plugging 6 and 8 into f double prime. So f double prime of 6, that's going to be 22 over 6 6 minus 7. 6 minus 7 all cubed, which is going to be, 6 minus 7 is negative 1. If you cube negative 1, that's a negative. A positive divided by a negative will give you a negative. And what that means, that f double prime, is a negative value, means that the function is concave down here. Oh, I guess I forgot to write in the infinity and negative infinity. But yeah, so what that means is that the function is concave down on this left interval, the one that goes from negative infinity up to the critical number of 7. And similarly, looking at 8 into f double prime, that's going to give you 22 over 8 minus 7 all cubed. 8 minus 7 is positive 1, right? So if you cube a positive number, it's positive. Positive divided by positive is positive. So f double prime is positive here, which means that the function is concave up here. So it's concave upward on this right interval that starts at the critical value of 7 and goes up to infinity. Okay, so I'll export this as a PDF and put it on Blackboard if you need it. But yeah, so we'll have our test on Tuesday.